Okay, continuing with our review problems for Chapter 5. Number 7. If $500 is invested at 8.3% interest compounded continuously, so here we're going to be using that formula for continuous compounding. A equals P times e to the RT. The $500 that we start with is the P. The 8.3% is the R, but remember we have to put it in as a decimal, so that would be 0.083, not 8.3. And after 4 years means the time t is going to be 4. So plugging all that in and doing the calculations, you should get 696.88, $696.88. Remember to make sure to take e to the 0.03 times 4, so you may need to put parentheses around that. Then part B, how many years will it take before you have $1,000? So the $1,000 is the A, the amount you end up with. How many years means we're trying to find T. So we're putting 1,000 in for A and solving for T. First, I will divide both sides by 500. Then I will get the e out of the way by taking natural logarithms of both sides. ln of e to the 0.083t would just be 0.083t, and that would be equal to ln of 2. Then go from 0.083t to just t by dividing both sides by 0.083. So t equals the natural logarithm of 2 divided by 0.083, and that comes out to be about 8.35 years. Number 8, how much would you have to invest now at 7.2% interest compounded quarterly, that is 4 times a year, in order to have $6,000 at the end of 5 years? So we're back to using the first formula because we're compounding 4 times a year. So that's this first formula where n is 4. The interest rate is 7.2%, so we're putting in 0.072 for R. 5 years means we're putting 5 in for T. We want to have $6,000 at the end, so A is 6,000, and the amount to invest now, the P, is what we're trying to find. So with all those numbers in place, it looks like 6,000 equals P times the number 1 plus 0.072 over 4 to the 4.5 or 20 power. So we got P times this other stuff. We want just P. So divide both sides by that other stuff. P equals 6,000 divided by that whole other thing, 1 plus 0.072 over 4 to the 20th power. And that comes out to be, to the nearest cent, $4,199.48. Now we're matching equations to graphs. We have these 4 equations. Can you see which one goes to this graph? Well, I notice there are no points on the graph with negative x coordinates. Remember that logarithmic functions like ln of x are undefined when x is negative. You can only take the logarithm of a positive x. So this is either C or D. Can you tell which one it is? Well, if you can't tell, notice what happens when x is 1. The natural logarithm of 1 would be 0. So if we were looking at equation C, when x is 1, y would be negative 0. If we're looking at equation D, when x is 1, y would be 0 plus 4. So we'd have a point on the graph where x is 1 and y is 4. So this is the graph of D. What about this graph? This looks like an exponential function. It is defined for all x. X can be any number. But y looks like is always positive. There are no negative y values. So it's going to be either A or B. Is it A? Well, with A, if I plug in 0 for x, 5 to the 0 would be 1. 1 minus 2 would be negative 1. And we would have a point on the graph where x is 0 and y is negative 1. But that's not what we have. So it's probably B. Just to double check, notice if x is 3, 3 minus 3 would be 0, and we'd get 1.5 to the 0 power. And any number to the 0 power is 1. So we do have that point on the graph where x is 3 and y is 1. This is equation B. What about this one? Here's another graph where there are no points on the graph with negative x coordinates. X cannot be negative. So this is another one of those involving ln of x. This one happens to be C. Notice that when x is 1, y is 0. And if x is bigger than 1, the natural log of x would be positive, but then we take negative ln of x and we get a negative y coordinate. Well, by process of elimination, you probably know which one this is. But just to double check, if x is 0, we get negative 1. If x is 1, 5 to the 1 is 5 minus 2 is 3, so we got the point 1, 3. Yeah, this is the graph of equation A. The number n of bacteria present in a culture at time t in hours obeys the law of uninhibited growth. N of t equals 2500 times e to the 0.015 t. A, determine the number of bacteria at time t equals 0 hours. So we're plugging 0 in for t. And you don't need a calculator for this because 0.015 times 0 is 0. E to the 0 is 1, because any number to the 0 power is 1. And then 2500 times 1 is 2500. So notice that at time t equals 0, that's like at our starting point, we get our starting value, our initial value of 2500. To determine the number of bacteria after 6 hours, now we're plugging 6 in for t. We do need a calculator for this. So it's just a matter of evaluating this function when you put 6 in for t. Make sure you do this yourself and make sure you do get the same number I got. So you're putting it into your calculator and evaluating it correctly, but you should get 2,735. And then when will the number of bacteria reach 20,000? So then we want to know what t has to be for n of t, the whole thing, to come out to equal 20,000. So set this equal to 20,000 and solve for t. Divide both sides by 2,500. Then undo the e with ln. Take ln of both sides and you get 0.015 t equals ln of 8. Then divide both sides by 0.015 and we get t equals ln of 8 divided by 0.015. And that comes out to be about 138.6. Number 11, a population is 7,000 in the year 2012 and 8,000 in the year 2017. Assuming it is growing exponentially, A, what will the population be in the year 2021? And B, in what year will the population be 10,000? Okay, we need to come up with our own formula here. Growing exponentially means it's like P of t equals some number times e to the some number t. And the number out in front would be like the initial value, the value for when t is 0. So we can make it easy on ourselves if we set it up so that our starting point is the year 2012, when t is 0. So t stands for how many years it's been since that starting point of 2012. That means that 7,000 is the initial population corresponding to t equals 0. Then when t is 5 years after 2012, that's 2017, that's when the population is 8,000. So 7,000 times e to the k times, we put 5 in for t, and that's equal to 8,000. Now we can solve for k. Divide both sides by 7,000. Get the e out of the way by taking ln of both sides. We get 5k equals the ln of 8/7. Then divide both sides by 5. K equals the ln of 8/7 divided by 5, which is about 0.026706278. When I do this, I like to store this in my calculator's memory so I can pull it back up. And then in 2021, that would be 9 years after our starting point of 2012. So we would plug 9 in for t and evaluate 7,000 times e to this number times 9. And that comes out to be about 8,902. Now part B, in what year will the population be 10,000? So we take that formula we got for the population, and we're trying to find what t has to be for that to equal 10,000. So set it equal to 10,000 and solve for t. Divide both sides by 7,000. Then take natural logs of both sides. Then divide both sides by 0.0267, that number. Here I have it in its original form. And I end up with 13.355. So t is approximately 13. And so we have to make sure we give the year. In what year? Well, when t is 13, that means 13 years after the starting point of 2012. And that gives us a year of 2025. Okay, last one. The half-life of a radioactive substance is 5.3 years. How long will it take for a sample to decay to 1% of its original size? So exponential decay means that after t number of years have gone by, the amount we have remaining is going to be the starting amount times e to the kt. T is the number of years, and k is the ln of 1/2 divided by whatever the half-life is. Here we are told that that half-life is 5.3. So the number that we use for k is the natural log of 1/2 divided by 5.3, which comes out to be about negative 0.130782486. So now that we have our function that gives how much will be remaining after t number of years, we need to set that equal to 1% of the original amount, 0.01 times a sub 0. We don't know what the original amount is, but that's okay because that divides out. The very first thing we do is divide both sides of this equation by that a sub 0. So it sort of cancels out. Then get the e out of the way by taking natural logs of both sides. And we get that this number for k, that was ln of 1/2 divided by 5.3 times t equals the ln of 0.01. Then divide both sides of this number by that, divide both sides of the equation by that number k. So t is the ln of 0.01 divided by that number, should come out to be 35.2. So that's how many years?